What is a coherent and incoherent source of light? If initial phase difference, let us say delta, between waves emitted by the source remain constant in time. Then we say that the beams are coherent. For coherent, it is not necessary that, let us say, this is beam 1, beam 2, they have to have same amplitude. No, they can even have a phase difference between them, but this phase difference should remain constant over a period of time, all the time. This should be constant all the time. Then we say that these two waves or beams are coherent. Now, next topic is diffraction of light. What is diffraction? Diffraction is bending of light around the corners. For example, if you take a slit and you have a source, light source, when it passes through this beam, it doesn't go straight, it bends. Similarly, when it goes here, it doesn't go like this, it doesn't go straight, but it bends. So this bending of light is called diffraction. Bending of light around the corners. These are the corners. Now, next topic is Fraunhofer diffraction at single slit. Now, this is the arrangement in the experiment. You have a slit. Just take another color. This is our slit. And there's a converging lens in between. And there's a screen put up at some distance from the slit. Here, a parallel beam is sent through this slit, and what happens is these beams interfere with each other, and at center all the waves are in phase. So right at the center there is a constructive interference, whereas as we go away from the center, there is a path difference which is created, and we can see that this path difference is created as we have seen earlier in double slit Young's experiment. If you see this diagram, this is the perpendicular that we draw. This is the extra distance that gets created, which is given as this one, because B is the full slit width, and we are talking about this triangle ABD. ABD, this triangle, basically this triangle. So we are using half of B. Okay. Now, the path difference between AP and BP. AP is if we take this path, or BP is if we take this path. This is a phase difference which we have seen. This is equal to B by 2 sine theta. Now for destructive interference, this path should be lambda by 2, right? And we know that at P, if we take this point as P, at P, all pair of rays from upper and lower part, upper means this portion and lower part means this portion, will give first minima at what place? The first minima is when B2 sine theta is equal to lambda by 2. Yes, we know that. Or B sine theta is equal to n pi for dark fringe. At P0, all the rays are in phase. So at P0, all rays parallel rays are in phase, which implies it will give you maximum or bright area. Here in this case, the point of maximum intensity lies nearly midway between successive minimas. Meaning thereby, if you have two dark fringes, the maximum intensity will be somewhere in the middle of these dark fringes. Now, in this case, electrical field at any point is given as E0 sine beta by beta, where this is an electrical field at any point, whereas this is electric field at P0. Okay. Now this is the amplitude. Both are amplitude. This is the amplitude at P0 and this is the amplitude at any other point P. Now what is beta here? Beta is given as half omega b sine theta by v. V is the velocity of light. Other terms, this is the slit width. Theta you have seen earlier in this diagram. This is the theta. And this is equal to b sine theta. Now we all know intensity is proportional to square of amplitude. So E naught dash by E0 square, this is the ratio. This will become the ratio of intensity at any point with respect to point P0. This will be equal to sine square beta by beta square. Now, if we plot this relationship, we get a plot something like this. At different points, this function is defined like this, whereas on this axis we have sine theta. And this is the ratio of I by I0. On this axis, we are plotting intensity. Now, this treatment we have seen, this was for diffraction by a rectangular. This slit here was rectangular. Now, what if this slit, instead of being rectangular, is a circle, small circle? Okay. Then what we'll see is bicircular slit. We have a circular slit of diameter B, and similarly, like previous experiments, we put a screen, and what we'll get is fringes made by this. Oh, sorry. We have this circular slit with diameter B. Then we have a screen placed at some distance D. Then the ray pattern will be something like this. And if we take this as a center line, let it make an angle theta with this. Now, this will make fringes in circular fashion because the slit was circular. So the fringes will look like something like this. You have a bright center, then a dark fringe, then bright fringe, then a dark fringe, then a light fringe, then a dark fringe, and so on and so forth. The center will be bright. Then you have, these are dark fringes. The radius R, if we define R as radius of diffracting rings, radius, if we take this fringe, then this will be the radius. Or if we take this fringe, then this will be the radius. This radius is given by 1.22 lambda d by b. Lambda we know is the wavelength of light. D is this distance between slit and the screen, and b is the diameter of the slit. Now, the mathematical derivation of this formula is beyond the scope of our study. We take it as it is for the sake of convenience. Next thing is limit of resolution. What is limit of resolution? Let's say we have a converging lens, and if we have source 1 here, source 2 here, we are going to form a diffraction pattern of its own, each source. Now, so long as, for example, S2 produces image 2, S1 produces image 1, so long as you are able to distinguish one image from the other, we will say the images are resolved. But what if they start coming close to each other? When they start coming close to each other, then we lose the resolution. We cannot distinguish one image from the other. Now, in order that image 1 and 2 can be seen separately, the condition is sin theta should be at least so much. And since we don't have to resolve the full image, even if half of the image is resolved from here and here, it is okay. So what we do is we don't take this theta we call as half angle. The reason is that when these patterns merge with each other, we'll get something like this. So long as even half of it we can resolve from this half of it, it is okay. That is why we are taking half angle as the angle of resolution, minimum angle of resolution. And what is B here? B is the radius of converging lens. And theta is also called angular radius of diffraction disk. Now, using this phenomena is very important, where the resolution is very, very important. For example, in microscopes and things like that, we take a case of a microscope wherein we have a converging lens. And what we do is, this is the focal length. We put an object just outside the focal length, and then what happens is the waves travel like this, and they make this image. Let us say this is distance f. This hole is angle theta. This is the diameter of central bright fringe, because at center all rays will be in phase, resulting into a bright area. Then you can write sin theta is equal to cancelling that. A is the radius of, this is A. This is also A for the converging lens. So this is minimum resolvable angle subtended by image at lens. This is the image, and this is the angle theta which is subtended at the lens. Now this is the minimum angle. If you have an angle subtended less than this, then you will not be able to distinguish the various part of the images. This is the minimum angle required so that the picture is clearly resolvable. Well, the next topic we take is reflection and refraction. Let's take a plane XY. This is X direction. This is Y direction. And a light beam in this plane strikes this interface surface. This is one media. This is another media. Now, we know that since this is a transverse wave, it will have motion in a plane which is perpendicular to the direction of longitudinal movement. For example, if I show it separately, if our wave is moving like this, then you take a plane which is this plane is perpendicular to the direction of propagation. Then the particles can move anywhere in this plane, but not outside the plane, like this. Now, if we superimpose, if we imagine this portion happening here, then what happens is that this wave will have components in XY direction. This double arrow components are components of electrical field in XY direction. And this dot, which will be perpendicular to it coming out of the plane of paper, is in Z direction. Now, when it reflects, and the reflected ray has a very peculiar property, and which is that the reflected light is weak in XY plane. For example, this was the amplitude of in the XY plane. Now it remains only this much, wherein the Z component, which was very small here, has become prominent here. So what happens in reflective light, reflected light, to cap it? The reflected light becomes strong in Z direction and weak in XYZ direction. Now, what happens to the reflected light? This was, as far as these two rays was concerned, this was reflection. And now, if it gets reflected in another media, then the refracted light is strong in XY media, and weak in Z direction. Okay. So we see in reflection, certain components are being filtered, and we will see this more in another topic called polarization. Now, here there's a term called Brewster angle. What is this? This when when reflected light is perpendicular to refracted light. Meaning thereby, in this condition, this is the reflected beam, this is the refracted beam, and this is the angle. If this angle becomes 90 degrees, then the angle of incidence is called Brewster's angle. And it is defined as mu of this medium. Now in light, we have another topic called Fresnel's distance. Also known as ZF. What is this distance? This is a distance for which ray optics is a good approximation. And it is given as where A is aperture width. Now, beyond this Fresnel distance, light beam tries to spread due to diffraction and becomes comparable to aperture width. What this basically means is that when light beams emerges from an aperture, we have seen due to diffraction, it tries to spread out. Now, if our this distance, let us say we take any point here, this distance Z, so long as this distance is less than our Fresnel distance, then the spreading of this beam is not very appreciable. But if we go beyond this, then the spreading of this beam becomes appreciable. So what it basically says that if your distances are less than ZF, which is defined by this formula, you're okay. There'll be a diffraction, but very little compared to the size of the beam. But if you go beyond this thing, then the beam will deviate much more than what is acceptable. Now, the next topic is polarization. We know that light wave is a transverse wave. Transverse wave means, suppose a wave is traveling in direction x longitudinally, then the movement of the particle will be along a plane which is perpendicular to z plus x, means perpendicular to propagation of wave. Now this direction could be anywhere, so long as it's like this way, doesn't matter which way, so long as it is in this particular plane. This is the normal way a light propagates, and these are the various components of these are the way the particles move. While the particles move in this plane, the wave propagates in some direction. Okay. Now, what if we take this example? This black wave, all the particles are moving in which direction? They are moving in vertically up or down. What about this one? All the particles are moving in horizontal direction. While the particles are moving in horizontal direction, like this, the wave is propagating in this direction. Similarly here, while the particles are moving up and down here, because particles cannot travel in direction of x. When particles move, it gives an appearance that the wave is moving in some direction. So for this black wave, the direction of particles is in this direction, while the wave is moving in this direction. Now, if you see in this wave or this wave, all the particles are moving in one plane. Yes. Okay. So we can say when the movement or displacement of wave, we are not talking about particles, of the wave, displacement of the wave, movement of the wave is restricted to one plane. The wave is polarized. For example, for this wave, there is no movement in any direction other than up and down, this way, which means in XY direction. This is moving only in XY direction. There is no component which is moving perpendicular to this. That means no component in Z direction. So such waves we call as polarized wave. Now, polarization can be achieved in various forms. One is, we have seen earlier, by reflection. What we have seen that if the wave is moving in XY plane, the reflected wave is strong in XY direction and weak in Z direction. So this is one way of polarization. Another way of polarization is by scattering of particles in the sky. When sunlight hits the particles in the atmosphere, sky, there is a scattering of light which causes polarization. And third is by means of polarides. What are polarides? They are actually thin films and their molecular structure allows that component of electrical field of light which is perpendicular to the direction of molecular structure of the polaride. This direction perpendicular to molecular chain is called transmission axis of polaride. I mean, in a layman's terms, if you let us say these are bars and there is an object which is a mixture of objects which some are like this, some are like this, some are like this. Now, when they are made to pass through this series of bars, what will happen? Only those ones which are parallel to it will pass through and others will be blocked. So this is polarization. That means the this bars actually is characteristics of polaride, which is due to its molecular structure. The molecular structure is such that it allows, for example, if we have this light propagating like this, this movement will be one direction. When this light passes through, this becomes sort of a filter. When it passes through this filter, those components which are parallel to it will pass through, and those components which are perpendicular to it will be totally blocked. Now, if you see here, this unpolarized light, this totally unpolarized light, when it passes through polarized structure, because of the direction of the direction of molecular structure, some light will pass through. Now, let's say we put another polaride which acts perpendicular to this, meaning thereby we have another pair of grids. Now, if this light which was polarized by the previous, this is polaride 1, and this is polaride 2. Then nothing will pass through. Everything will be blocked because now this component of light is completely perpendicular to the grid, which will not allow anything to happen. So here, the light is totally polarized. What happens if the light coming after first polarization or first polarization itself, instead of being, to make things easy, let's say this is polaride 1, which allows only the vertical movement of the wave. Now the second polaride, instead of being parallel, is at an angle. So what happens? Some movements will get passed. Some. It will not be completely blocked because it's not perpendicular. And this we can characterize or quantify by an expression called law of Malus, which says intensity of the light coming out of a Polaroid is defined as initial intensity cos square theta, where theta would be theta will be this angle. This angle will be theta. So I naught is the intensity of light when incident electrical vector is parallel to transmission axis. We can call this as, in this Polaroid, we can call this axis, this as axis of polarization. Sorry, transmission axis.